We saw in the last video that we want to start using sample statistics to estimate our unknown population parameters. And so that's exactly what we're going to do. We're going to come up with our first formula for a confidence interval. This is going to be the confidence interval for a population proportion P. So when you want a population's proportion, you're going to use a sample proportion to estimate it. Now the sample proportion is P hat. That's your point estimate right here, which was what we said right here. That's your P hat. That's your point estimate. And then your critical value is Z alpha over 2. That's what it's called. Remember, we saw that terminology, critical value, back in chapter 7, and we'll play around with it in another page or so. And then the square root P hat 1 minus P hat over N, which should look familiar because without the hats, that's very much what we were estimating sigma to be back in section 8.2. All right, now if you're going to use this confidence interval, there are some requirements that you have. First of all, it has to be a simple random sample of size N. Like everything in this class, we basically only work with stuff that is random. And of course, true random is hard to come by, but we're going to assume we have it anyway. Then we're going to have an independent sample. So if it's independent to begin with, great. If we're sampling without replacement, right? So when you draw, but you don't let that person back in the pool. So for example, proportions get used a lot of times for phone surveys. So I call people up and I say, what do you believe, I don't know, in giving away a Halloween candy? Yes or no? And then I find out what proportion are going to give away Halloween candy that year. So if I'm sampling without replacement, that means when I call a person, I'm not going to call them again. So I call every phone number individually, but I don't ever repeat. So that's sampling without replacement. So if you're going to do that, you have to have a small sample size. Otherwise, you're affecting what's left. And the analogy I gave back in chapter 8 was thinking about drawing M&Ms from a large vat of M&Ms. Right? If you draw 30 M&Ms, or in this case, because this is for proportion, you're not going to want 30. You're going to want n times p times 1 minus p to be bigger than 10. So, let's say you're doing 200 M&Ms. So you draw 200 M&Ms, that's going to be a lot of M&Ms. That's going to be a lot of people you're calling, right? You want 500 people. So what you want to do is make it out of such a much larger population that just calling those 500 people doesn't fundamentally affect what's left. All right, so then the margin of error for one proportion confidence interval, that's the margin of error is the back half of that formula, because remember it's the point estimate, p hat, plus or minus your error. So the Z alpha over 2 big square root thing, that's your error, which is half of the width of your interval. Now, sometimes we'll use the formula part of this, right? If we have p hat and all of that, and we'll go through all the trouble of finding the formula. If we're given the interval, however, it's just easier to think of it as half the interval width, right? That's kind of simpler. So you use whichever is more convenient for you. All right, now just a quick note, there is some difference here between what we saw in chapter 8 and what we're using now. So in chapter 8, so let me bring up chapter 8 real quickly. There we have it, chapter 8, 8.2 in particular, the central limit theorem for proportions. You can see that the standard error, which was sigma, right, p hat, was the square root of p times 1 minus p over n. Well, that's all well and good, except we don't know what p is, so we can't really use it. We can only use p hat, oops, not that one, in our particular example. And that's what this is saying. So your formulas get modified slightly. And also your requirements for using all of this. Remember, in here we said it was n times p times 1 minus p, but in real life we don't know what p is for a non-probabilistic distribution, right? So probability distributions, you technically know what p is because you assume it to be a certain thing. But here we can't make those assumptions because that's the whole point of this chapter. So that means we're going to have to use p hats instead of p's for those two formulas. Now you can use your calculator to find all of this confidence interval stuff, and we're actually going to do that as we do some problems. So this is just for reference for later. So now we want to tackle the critical Z values, that portion of the formula, the Z alpha over 2 portion that we saw a little bit in chapter 7, but we're now going to see it again. Okay, so let's remind ourselves from chapter 7 what we saw. Critical values are labeled Z with a little subscript after it, which we give the Greek letter alpha as that subscript. And that's a critical Z value. It's where alpha is the area in the right tail. Now the right tail part doesn't change. That's by definition, it's the right tail. And we're going to use single tail values like this in chapters 10 and 11, where you have one tail and the area is the whole thing in that tail. The ones we're going to need for chapter 9, however, are going to be a little bit different because I don't know if you noticed, but there was this alpha over 2 business. Here, if I go back to the formula, see this? See the alpha over 2? So what does that mean? Well, when you look at a critical value for a single tail, it puts the whole alpha in the right tail. But for a confidence interval, you're going to have your confidence interval in the middle. And what that means is you're going to have to split your alpha in half. Put half of it over here, alpha over 2, and half of it over here, alpha over 2. And that'll get you 2 critical values, one on the right and one on the left. They'll be the same number, but they'll be opposite signs due to symmetry. So one will be positive, one will be negative. And the way to find those critical values, if you remember from chapter 7, is using inverse norm. Remember, because these are z values, that means this is a z curve. So the mean is 0 and the standard deviation is 1. So those will be what you'd put in the back end of your inverse norm. Or you can use the bottom row of your t-table, which we'll talk about later. All right, so now let's go find some with our lovely in calculators. So here we have, I'm going to make this picture a little bit bigger for us to see here. So we want to find the critical z values that correspond to a 95% confidence level. Okay, so our first mission in life is to try to figure out what alpha is. So if the center is 95%, then alpha is 1 minus that. And that comes from right back here. If you look at the formula, oh, sorry, I got to scroll back up here. It says 1 minus alpha times 100%. That's your confidence level. In other words, the confidence level and alpha are complements of each other. I'll write that down here for you guys. There we go. Alpha and C level are complements. And I mean complement there in the terms of the same thing we saw in chapter 5, the complement rule for probability, because these are essentially probabilities. Not really, but we can think of them that way. Okay, so then alpha is 1 minus 0.95, which is 0.05. So that means alpha over 2 is 0.05 over 2, which would be 0.025. Okay, so that's what I put in each tail. So each tail is 0.025. All right, now I need to find my critical values, and you can actually find either one because they're essentially the same thing. Okay, so the one on the right is positive, the one on the left will be negative, but that's about it. There, and I just threw in a negative symbol right there. Okay, so according to these instructions right here, I need inverse norm, left tail area, 0 and 1. So let me do that. Inverse norm. Now the left tail area. Okay, so for the one on the left, it's 0.025. There we go. For the one on the right, it would actually be 0.975. So let me just show you. Inverse norm, 0.975, comma 0, comma 1. Okay, why 0.975? Well, you add up 95.95 plus 0.025 because the one on the right has all of that area to the left. Now, if we do this right, they should be the same number. So I'm going to pull up the calculator here. Let's see here. I'm going to move it over just a little bit so we can see it. Okay, so I'm going to type inverse norm. So second distribution, number 3 is inverse norm. I want to take 0.025, 0 and 1. Go to paste and press enter, and then press enter again. And I get negative 1.5996, which would round, if I'm doing 3 decimal places, which I am, to negative 1.960 and positive 1.960. So let me show you the other one. If I did it again, inverse norm, but instead of using 0.025, I use 0.975, just like I said. That's the other one, right? And do you have to show both of them? No, you don't, right? You just have to be able to find one of them. So whichever one you find is totally fine, right? So find the left-hand one, find the right-hand one. It doesn't make any difference. And then I just labeled the 2 of them there so you guys could see it. So negative z.025 is negative 1.96, and positive z.025 is positive 1.96. And to be honest with you, what we do a lot of the times for these ones is we actually type plus or minus. There we go. So the z plus or minus z.025 is actually plus or minus 1.960, and those would be our 2 critical values that they were asking for. Right there. All right, so now we're going to do it all again, but this time alpha is 0.005. Okay, so let's see here. Remembering that alpha and our confidence level are complements of each other. So let's see, alpha was 0.005. That means that alpha over 2 is 0.0025, right? Because you take 0.005 and divide it in half. So that's a starter. And then we also know that our confidence level, our C level, is the complement of alpha. So that's 1 minus alpha, which is 1 minus 0.005, which would be 0.995. So our confidence level, which is actually one of the questions they ask, is what's our confidence level? It's 99.5% or 0.995. So I'm going to box that because that's one of our answers right there. Okay, so our confidence level is that. So now we need to be able to find those two values. So there's two of them, the one on the left and the one on the right. And I've labeled this here so you can see. So 0.0025 on the left, 0.0025 on the right, 0.995 in the center. So I'm going to need the left tail area, which is 0.0025. So let me grab a calculator. Go to inverse norm, which is above in the distribution menu above the variables button. And I want 0.0025. Enter. And paste. And I get negative 2.807. Oops, let me make this larger so you guys can see it here. And that would be 0.0025, as opposed to the one above, which is just 0.025. Now, what about the one on the right? Well, the area to the left is 0.995 and 0.0025 together. You don't have to do this, though. You can actually just use the one you've got. But if you wanted to do it the other way, you'd have to do like this, and then do inverse norm with that as your area. So number 3 and 0.9975. Go down to paste. Press enter, enter. And that gets you positive 2.801. But you actually don't need to bother with that. I mean, once you find one, you've found them both, because what they're going to be is opposites of each other. So it's plus or minus 2.807. And there we have it. So we don't need to use the calculator to find both of the critical values. We can actually just use it to find one of them, and that's fine. That'll work well enough. Once you have one, you know the other one's there by symmetry. Oop, there we have it. It just occurred to me I should really only box the answers, so I'm going to do that and get rid of this box and just make it an underline real quick. All right, there we have those two. All right, now what about this one? Find z sub 0.065, and what confidence level would use that as a critical value? Ooh, good question. Okay, so let's see here. I'm going to get rid of this note here for myself. So alpha is 0.065 on this one. That's the area in the right tail. By definition, when you see that little subscript, z 0.065, according to the picture right back here, when you see that, that is automatically an area in a right tail. And because it's a confidence interval, it's actually alpha over 2 already. It's not technically alpha because this is for a confidence level. So we know that alpha over 2 is actually 0.065. No, 0.065. Okay, so this is alpha over 2 is 0.0065, or excuse me, 0.065, and that's the area in the right tail or the left tail, right? Same thing. So what I did was I labeled the two tails 0.006, I did it wrong, 0.065. I keep throwing an extra 0 in there. So it's 0.065 here and 0.065 on the other side. Okay, then what you have to do is figure out the area in the middle, just for labeling purposes if nothing else, but it'll also tell you what confidence level it would be. Remember that your alpha and your confidence level are opposites of each other. So if alpha over 2 is 0.065, then alpha is 0.065 times 2, which would be 0.065 times 2, and that's 0.13. Okay, so let me put that in here. So that's your alpha, 0.13 right there. So that means that our confidence level, remember they're complements of each other. So the confidence level is 1 minus alpha, which is 1 minus 0.13, which would be 87. 1 minus 0.13 is 0.87. So it'd be 87% is our confidence level. And I'm going to leave that box because that's one of the answers that we were looking for. I lost my percent sign there. Okay, so that means that this center portion I have here needs to be labeled with an 87. There we go. So 87% in the middle, 0.065, 0.065. And those three numbers should add up to 1 if you do it correctly. Okay, so now I just need one of the z-scores. Once I know one, I'll know the other. So I'm just going to find the one on the left because it's easier. And I'm just going to find 0.065. So let me grab the calculator. Inverse norm, number 3, 0.065, 01. So I'll go to paste and press enter. And I get negative 1.514. There we have that. So that means that our two values, oh, I should have labeled this. This is 0.065. So that means that our two critical values would be 0.065, and that would be 1.514, like that. And there we found both critical values as well as what confidence level would actually have used those critical values. And we did that here and up here. Just remember that the alpha level and your confidence level are complements of each other. So if you know alpha, then you know your confidence level because they're going to be opposites. Here you didn't know alpha, you actually knew alpha over 2, and then you multiply it by 2 to figure out your alpha right here. And then from there, you'll figure out your confidence level. And we're all done with that video. I'll see you back here for more in